All right, you've made it all the way to compound machines. So the four big things in our kind of long video is number one, learn how to calculate the IMA of a compound machine from all of the little individual simple machines. You're going to know how to calculate the AMA of a compound machine. You're going to have some special example calculations that you can use as a little template. And then last but not least, the big no-no for compound machines, something that we never, ever do. Ever.
So our compound machines are essentially just simple machines that are all working together to complete some sort of a task. A bike is a great example. There's wheel and axles in there. There's gear trains. There's a lot of good stuff. Now, to calculate the mechanical advantage of a compound machine, all you need to do is find the individual mechanical advantage of the simple machine inside of the compound machine and multiply them together. And that's it. So if you have a compound machine that's made up of a lever connected to a wheel and axle connected to a pulley, you would just treat all three of those as individual parts, calculate their mechanical advantage, and multiply those three together. So let's look at some examples of how this might actually work. So let's focus on pulleys since they're pretty easy to calculate as far as IMA goes. So over on the left side, we have a pulley system. And notice this is not a block and tackle because a block and tackle would have one string that kind of weaves between all of these. Here we've got one string, we've got two strings, we've got three strings. So this is a compound machine because we have three different pulleys in the system. So let's calculate the IMA of each of those. So for a compound machine, we know that we just multiply those mechanical advantage together, so we can do that for IMA. I'm going to look at the mechanical advantage of this first one, and it looks like it's connected to the ceiling, and we're pulling over on the right side, so we have a mechanical advantage of 2 because we have a movable pulley. Looking at this one, it looks like the same thing. We're connected to the ceiling. We have a movable pulley. Same thing with that third one. We are connected to the ceiling. We have a movable pulley. So we have 3 movable pulleys. So I know that the mechanical advantage of the first one is 2, of the second one is 2, and of the third one is 2. So to find my total mechanical advantage, I just need to multiply all 3 of those together, and we find that the mechanical advantage for this system of pulleys is 8 because I took each pulley separately, multiplied them together, and got my value. Let's look at a little more complex version of this. Same idea. We got to figure out what simple machines are acting in our system, and then we can figure out what the overall mechanical advantage is. So it looks like we have a weight that is pushing down in this direction. We've got a lever. We've got a pulley. So let's kind of break that down into parts. So for my pulley, or I already know that this is a movable pulley, so I know that the mechanical advantage of this guy has to be 2. To find the mechanical advantage of my lever, I'm going to take my DE over my DR. So my effort distance is from the fulcrum all the way to where that force is acting, which is 12 feet, divided by my resistance distance, which is from the fulcrum to the resistance force, which is 4 feet. So if I plug that into our equation, we've got 2 from the movable pulley. We've got 12 feet over 4 feet from the mechanical advantage of the lever. All we have to do is multiply those out, and we find that the mechanical advantage of this whole compound machine is 6.
So again, for IMA, we need to figure out the IMA of all the individual machines and multiply them together. Luckily, AMA is quite a bit easier. So if you remember, our AMA equation is your FR divided by your FE. So all we need in practice is the weight that you're trying to lift, your FR, divided by the effort force that you are applying at the end, and that is it. You do not need to split it up into simple machines. You just need the weight, your FR, and your final FE.
Not too shabby. So we're just taking the same skills that you've been working on. We're just combining them all together for compound machines. Now, gear ratios we need to watch out for because we cannot mix mechanical advantage and gear ratios. They are two different things. So if we have a compound machine that's made up of gears and simple machines, we need to report gear ratio and mechanical advantage separately. But what's really, really nice is the equation is essentially the same. To find the total gear ratio of a compound machine, we just find the individual gear ratios of the gear trains within the compound machine, multiply them together, and we're good to go. Notice how it's the exact same equation. It's just gear ratio instead of mechanical advantage. So mechanical advantage is essentially like a force multiplier. So we can see if I put in 1 pound of work, how much force am I going to get out of the deal? Same thing happens for gear ratio. If I were to put in a certain amount of torque, an input, by multiplying by that gear ratio, that tells me how much torque I'm going to get out of the deal. But again, our equations for calculating compound machines is the same. We just separate mechanical advantage and gear ratios from each other. So let's do a quick example of what that might look like. And I'll kind of talk through my strategy of working through this problem. So we've got this freaky thing. The first thing I'm going to do is just kind of figure out what the heck does this machine even do. And it looks like I'm going to apply a force to the edge of this lever arm, which is going to rotate my gear train in the clockwise direction, which makes my gear down here move in the counterclockwise direction, which in turn lifts up that arm over there. So it seems like a lot of work just to lift up that arm on that other side. But whatever, this is for practice. So I need to identify, number one, what are the simple machines that make up this compound machine, predict what the machine will do, and then we can break it down and actually calculate this out. So if I look at this first part, so we have this arm attached to a gear, really what that's acting like is not a lever arm, it's acting like a wheel and axle, where the wheel is that big rotation of the metal Vex arm, and the axle is the gear, which is kind of a counterintuitive way to think about it. So the first machine is a wheel and axle. The second machine is a gear train because we have meshed gears right here. And then the third one, looks like we have another wheel and axle where we have the wheel as the little gear and our axle essentially as that really big rotation. So we've identified the 3 mechanisms within the series. Let's break it down and do some calculations to figure those out. So let's focus on our wheel and axle based on the information that we have. So we have our distance from the center, that rotation point, to the edge of our arm. We also have the radius of our gear. So let's use that just like we've done before. My IMA is dE over dr. So my dE, my effort distance, what I am putting effort into is the lever arm essentially. So I'm going to put that as 4 inches up top. And my gear is going to be essentially that axle piece, which is 1.5 inches. So we find that the mechanical advantage, or the ideal mechanical advantage of the first wheel and axle, is 2.67. So let's move on to the little gear train right there. Now remember, you cannot mix mechanical advantage and gear train, so we're going to do that separately. So we know the number of teeth. We can also use the radius or the diameter. We'll come up with the same value. But I'm going to pick my gear ratio equation of teeth out over teeth in. So if I ignore the little lever over here, I'm looking at my input. I'm putting the force into that first gear. I'm getting output from the second gear. So I'm going to put the teeth of the first gear because I'm putting force into that, into my input. And my output is that little gear down below, and we find that the gear ratio is 0.4. So now we just have one more to do. We've got that last wheel and axle, so let's do a quick calculation there. Our effort distance is going to be that gear because that's essentially where the force is being transferred. And the resistance is going to be that last little arm right there. So follow where the force is acting and what's happening because of that force. So I'm going to use my radius right here, which is 0.6 inches. And I'm going to plot that in for my effort distance because that's essentially what's generating the force from our perspective, divided by the 4 inches of that last chunk. And we get 0.15 for my ideal mechanical advantage. So then our very last step is I'm going to take my 2 mechanical advantages from the wheel and axle and multiply them together, which is 0.4. and I'm going to have my gear ratio, which is only one train, as 0.4, and I am always reporting them separately. So remember, when we are dealing with mechanical advantage and gear ratio, always report them separately. Never, ever, ever, ever multiply mechanical advantage and gear ratio. Just report them as two separate numbers.